This video is a part of an online course on algebra and will be about identities on sets. In set theory, there are several fundamental operations that you can do to sets. The chief among them are the union A union B, the intersection A intersection B, set difference written either like A by B or A minus B. Both notations are commonly used and I will use both of them in this course, and complementation A complement. These operations help in understanding the relationship between various sets. Now, let us go into the details of these operations. The union of two sets A and B denoted by A union B, usually that union is written like a cup, but sometimes we may use variants like a square cup. I will come to that when the moment arises where I need to use a square cup. So, the union consists of all those elements that belong to either A or B or both. Notice that in mathematics the OR is always inclusive OR, but for emphasis I have written either A or B or both. So, that means A union B is X such that X in A or X in B. That is the definition of a union. Now, if this suddenly makes alarm bells ring in your head, yes, there is a slight problem. Recall that the typical way by which we define a subset of a given set is to say something like X in A such that P of X, where P is a property on the set A. Now, this notation gives you precisely those elements in A for which P of X is true, but this is somewhat different from the definition of A union B we have given. We have given only the head, the tail is missing. It is X such that X is in A or X is in B. Where is X supposed to come from? This definition of sets via properties, it is crucial that the property is defined on a set, otherwise you might run into problems. For the time being, just take this for granted. In a later video, I will briefly explain some of the subtleties of set theory. The key point is we are taking a naive approach to set theory and we are not being concerned about the various paradoxes and contradictions that can arise if we are not careful. As I said, reading Halmos's book Naive Set Theory, even though the title says naive, the book is not at all naive. You will have a better understanding of what is going on. In any case, wait for the later video where I sort of slightly get into the troubles that can arise and also about how you can rectify such things. But for the time being, take it for granted what union is. I am sure you have already encountered the notion of union in your school. It is just a way of combining A and B. It is saying both elements of A and elements of B are put together in this one basket. Here is a picture about the union. Such things are called Venn diagrams. These are Venn diagrams. They are very useful in describing relationships between sets. So, here you have shaded the set A, here you have shaded the set B, and A union B is just combining them both, a rather simple Venn diagram. Now, we come to the next operation or way of combining sets, that is intersection. The intersection of two sets A and B, denoted A written upside down U B, consists of all elements that belong to both A and B. That is, it is X such that X is in A and X is in B. Again, you might wonder, well, there is a trouble here, where is X supposed to come from, but fixing it for the intersection is not that difficult, you can do it yourself. Think about how you can write, write this properly as X in some set such that X is in A and X is in B. You can write a proper definition if you think about it. Now, one thing that you might have noticed if you are an eagle eyed careful listener is that In the previous videos, I had used the notation x colon something, and now I am writing x line something. Well, both notations are commonly used, so I will interchangeably use either of them as per my mood. This is also perfectly legal. And of course, we have the Venn diagram for the intersection. You have set A, you have set B, the intersection is the set of common points. Now we come to set difference. It is not that difficult to understand. The set difference A minus B consists of all elements that are in A, but not in B. So, again it is x such that x is in A and x is not in B. And here is the Venn diagram. This is not the Venn diagram of set difference, this is a Venn diagram of the complement. What is the complement? The complement is a special case of set difference. In most contexts, we have a particular set U, and every single set we consider will be a subset of U. Okay? When we just say the complement of A, what we really mean is the set difference with respect to the set U. That is, it is the set of all those elements in U that are not in A. In a course on number theory, the universal set is usually the set N. Almost all sets that you consider in a course on number theory will be subsets of N. In a course on calculus, it is often the set R. All the sets you consider will be subsets of the real numbers. So, in notation, A complement is the set of elements x in U such that x is not in A. More elaborately, if you want to write, this A complement is the same as U minus A. Now, let me emphasize again, it is dangerous to use the complement of a set in contexts in which it is not clear what the universal set is. If you do not know, or if there is some ambiguity as to what the universal set is, you might mislead your audience. They might consider a different set as the natural universal set, and you might be thinking of a different set. It is somewhat dangerous. So, as much as possible you can try to avoid complements, but nevertheless it is very useful because you will usually be in a situation where there is a clear cut universal set. Now, coming to the main topic of this video, which is set theoretic identities. That is, these unions, intersections, set difference, complements behave with respect to each other and satisfy some natural identities. All of these are somewhat trivial and straightforward to prove. So, last video we saw things like proof by contradiction, proof by contrapositive, proof by cases. You won't need any of those in proving these. These are all straightforward. Let me just quickly run over them. The first one are called idempotent laws that just say that A union A is A and A intersection A is A. This is something that is so obvious that it does not even deserve a proof nor a fancy name like idempotent law. The second one, domination law, sounds very fancy and intimidating, but all it says is A union U is U, where U is the universal set, A intersection empty set is empty. Again, utterly trivial to prove. So are the commutative laws. A union B equals B union A, A intersection B equals B intersection A. This more or less follows from the way we have defined OR and they are sort of symmetric. Associative laws. If you take A union B first and then join to it the elements of C, it is the same as first joining B and C together and then joining A. This is also utterly obvious to show, and a similar identity involving intersections. Finally, one slightly less obvious result is the distributive law. A intersection B union C equals A intersection B union A intersection C, and A union B intersection C is A union B intersection A union C. Now, for some satisfaction, let us see just one proof of one of the identities. It is not really hard proof, it is just 3 lines. I am going to show one of the distributivity laws. Suppose x is in A intersection B union C. The goal is to show that X is in A intersection B union A intersection C. Then by definition X is in A and X is also in B union C. This implies that X must either be in B or in C, it could possibly be in both also. Now, if X is in B, then X is in A intersection B. Well, if X is in C, then X is in A intersection C. In either case, X is there in A intersection B union A intersection C. So, we have shown that starting with an X in A intersection B union C, that same X is in A intersection B union A intersection C. Have we proved the distributivity law? No, not technically. What we have really shown is that A intersection B union C is a subset of A intersection B union A intersection C. We have not really shown equality, but if you think about it for a second, we can reverse the steps exactly the same way, traverse the opposite path, start with an X in A intersection B union A intersection C, and you will realize that you can show that X is in A intersection B union C. Consequently, both sets are equal. Now, we come to somewhat non-trivial laws, set theoretic identities. These are the famous De Morgan's laws. Now, I am going to state and prove only the simplest case of De Morgan's laws. There are cases where you have arbitrary union, arbitrary intersection, but they are just trivial variants. I am just going to focus on the simple case where you have just two sets. The complement of A union B is the same as A complement intersection B complement. Analogously, the complement of A intersection B is the union of A complement and B complement. Okay? Now, notice that means I am assuming that there is a universal set U involved. Now, if you carefully go through the proof and understand it, you will realize that you do not really need to state De Morgan's laws using complements. You could have stated it for set difference as well. I will leave it as an exercise for you how to state it for set differences. So, let us prove one of these De Morgan's laws. Let X be an arbitrary element in the universal set U. We will prove both directions of the equality. That means, we will show containment. To show such set equality, you have to show two directions, you have to show subset and superset. So, first we will start with an element in A union B complement. The aim is to show that X is an A complement intersection B complement, which means A union B complement is a subset of A complement intersection B complement. Okay. What is the meaning of X is there in A union B complement? This means X is not in A union B, right, because it is there in the complement of A union B. In other words, X is not in A nor is it in B. Since X is not in A, it belongs to the complement of A, and in an entirely similar way X is not in B, therefore, it belongs to the complement of B. That immediately tells you that X is there in A complement intersection B complement. Now, coming to the reverse direction, start with an X in A complement intersection B complement. This means that X belongs to both A complement and B complement, which implies that X is neither in A nor in B. Okay? Therefore, it is not there in A union B, and therefore, X is in A union B complement. The final conclusion is A union B complement is A complement intersection B complement. I hope this short proof convinces you of two things. First, set theoretic identities are extremely easy to prove, and number two, set theoretic identities are extremely boring to prove, but unfortunate you have to spend some time proving some of these identities. Thankfully, the hardest part is over. This is the toughest identity we need for the time being, and we have spent some time proving it. I am going to leave it to you to prove the other identity, that A intersection B complement is A complement union B complement. Here is a simple Venn diagram illustrating De Morgan's laws. Have a nice look at it. Because it is bright, it might wake you up from the boring proof we just saw. Okay. Now, we have seen the basic set operations, we have seen some basic set identities. Now, as I said, in this course almost every object that we consider will be a mathematical object, every set we consider will be consisting of mathematical objects. However, sometimes it is usual to have a few real world examples, just go through them once, so that these operations and identities are fixed in our minds once and for all. So, I am going to give some real world examples. These are all rather trivial. If you are thoroughly understood the previous slides, I strongly recommend that you stop the video now and move on to more interesting things, but I am going to spend some time giving some real world examples of set theoretic operations and identities. So, if A represents students who play football and B represents students who play basketball, then A union B represents those who play either football or basketball or both. For intersection, if A represents people who speak English and B represents people who speak Spanish, then A intersection B represents people who can speak both English and Spanish. If A represents the class of students and B represents those who have completed the assignments, A minus B are the delinquents. These are students who have not completed their assignments. Finally, to take an example of a complement, if U represents all citizens of a country and A represents those who are employed, then A complement represents unemployed citizens. Now, let us see some examples of identities. Again, I apologize, they are all highly trivial, but nevertheless let us go through them. Suppose A represents students in a math club, B represents students in a science club and C represents students in a literature club, then A intersection B union C represents students in the math club who are also there in either the science club or the literature club. And here is an example of De Morgan's laws. If A represents rainy days and B represents days with outdoor sports events, then A union B complement represents days that are neither rainy nor have outdoor sports events, which is the same as A complement intersection B complement. Here you can see that I mean, just from this example you can see why De Morgan's laws are true. Finally, there is a complementation law. The complement of the complement gets you back to the original set. If A represents all members of a gym and A complement represents the non-members, then the complement of the non-members is clearly those who are members of the gym, which confirms that double complement returns you to the original set. This is a course on algebra and you have just watched the video on set theoretic identities.